Hey, welcome to The Explainer. Today, we are diving into one of the most bizarre and honestly most powerful states of matter that we know of, superconductivity. It's this incredible world where the basic rules of electricity just seem to, well, they seem to bend, promising all sorts of tech that feels like it's been pulled straight out of science fiction.
So just think about this for a second. What if you could start an electrical current and it just kept going, like forever, with no resistance, no energy getting lost as heat, nothing? That isn't some fantasy. That is the fundamental promise of a superconductor.
And this is where the whole story begins. Back in 1911, a physicist named Heikki Kammerling-Onnes was playing around with mercury at ridiculously low temperatures. As he cooled it down, its electrical resistance went down, which is pretty much what you'd expect. But then, at 4.15 Kelvin, we're talking minus 269 degrees Celsius here. Something completely wild happened. The resistance didn't just get low, it vanished. It just fell off a cliff, straight down to absolute zero.
Now, zero resistance. That means perfect efficiency. In a normal wire, you've got electrons bumping into atoms all the time, which creates friction and wastes energy as heat. But inside a superconductor, they just glide through effortlessly. You could actually start a current in a superconducting loop, take away the battery, and that current would just keep flowing, theoretically, for hundreds of thousands of years.
Of course, right? A property this amazing couldn't be that simple. It turns out achieving this perfect state is, well, it's incredibly fragile. Superconductivity can only exist within a very, very specific set of boundaries.
And these boundaries are what we call the three critical limits. You can think of them as the three golden rules you absolutely cannot break if you want to keep the superconductivity going. Break just one of them, and poof, the magic is gone.
Okay, so first up, and this is the most famous one, is the critical temperature. Every single superconducting material has a unique temperature threshold. If you go even a tiny fraction of a degree above it, it just snaps right back to being a normal, everyday material with resistance. For that original mercury sample, that temperature was just a few degrees above absolute zero. Incredibly cold. Second, you have to be really careful with magnetic fields. If you put a superconductor in a magnetic field that's too strong, it will actually destroy the effect. Every material has its own breaking point, its critical magnetic field. Push past it, and that perfect conductivity just vanishes. And finally, there's a limit to how much juice you can actually push through the thing. See, any electrical current generates its own magnetic field. And if that current gets too intense, the magnetic field it creates can actually become strong enough to break the superconducting state from the inside out. That limit is called the critical current density. So when you put these three limits together, temperature, magnetic field, and current, they create this sort of three-dimensional safe zone. Superconductivity can only exist inside the little bubble defined by these three factors. If you push too high on any one of them, too hot, too strong a field, too much current, the material pops right out of that zone and goes back to being normal. For about 20 years, everyone thought that zero resistance was the whole story. But then, in 1933, two scientists, Meissner and Oxenfeld, stumbled onto something else, something arguably even weirder. They found that when a material became a superconductor, it didn't just stop new magnetic fields from getting in, it actively kicked out any magnetic field that was already inside it. This incredible phenomenon is called the Meissner effect, and it is the secret ingredient behind one of the most mind-blowing things you can see in a physics lab, magnetic levitation. Just look at the difference here. On the left, magnetic field lines just pass right through a normal material. No big deal. But look at the superconductor on the right. It completely changes its behavior. It forces those magnetic field lines to go all the way around it. It essentially becomes a perfect magnetic shield. The technical term is perfect diamagnetism, but magnetic shield is a great way to think about it. So what happens when you bring a magnet near a superconductor? Well, the superconductor pushes that magnet's field away, creating an equal and opposite magnetic force. And this repulsion is so strong that it can easily overcome gravity and just lift the magnet, leaving it floating in midair. It looks like magic. Now, to actually use any of these crazy properties in the real world, we needed materials that were a lot tougher, ones that could handle more extreme conditions. And this led scientists to classify two completely different types of superconductors. So you've got two main families. Type 1 superconductors, like the early ones made of lead and mercury, are called soft. They show that complete Meissner effect we talked about, but they're very fragile. A pretty weak magnetic field will knock them out of their superconducting state. Then you have type 2, or hard, superconductors. These are really clever. They actually allow a little bit of the magnetic field to penetrate through them in these tiny, tiny little filaments. And this trick allows them to stay superconducting in much, much more powerful magnetic fields. And that's why these type 2 materials were a total game changer. Their ability to handle really intense currents and incredibly strong magnetic fields is what finally unlocked the door for pretty much all of the modern high-power technologies that use superconductors today. So where can we actually see this incredible physics at work? Well, the applications are some of the most advanced pieces of tech we've ever built. I mean, the most famous example has to be the maglev train, right? They build these insanely powerful superconducting magnets right into the train itself. These create intense magnetic fields that push against the track, lifting the entire train clean off the rails. With zero friction from wheels, these trains can hit incredible speeds, just gliding along on a magnetic cushion. But it's not all about raw power and speed. Superconductivity also allows for extreme sensitivity. A perfect example is something called a SQUID. That stands for Superconducting Quantum Interference Device. And it uses the quantum weirdness of superconductors to become the most sensitive detector of magnetic fields that has ever been created. Period. And that incredible sensitivity has some revolutionary uses. Squids are so precise, they can pick up on the teeny tiny magnetic fields generated by neurons firing in your brain. That's how we get those advanced MEG brain scans. They can detect microscopic shifts in the Earth's crust, find tiny flaws in airplane parts, and even measure the magnetic fields of our own organs. When you really boil it all down, superconductivity is more than just a cool party trick. It's this rare, beautiful example of quantum mechanics, the strange rules that run the subatomic world, actually showing up on a scale that we can see and touch and use. We're talking about everything from levitating trains to literally mapping our own thoughts. But that massive challenge has always been the cold, the need for all this expensive, complicated cooling, which, of course, leaves us with the ultimate question, the holy grail of this entire field of physics. What could we build? What problems could we solve?